Welcome everyone to the Connecting to Loopring Bridge workshop. Joining us today is Brecht. And yeah, I'm going to hand it over to him to give a quick introduction to himself and kick the session off.
Okay. Hey, everybody. I'm Brecht. I work at Loopring. I'm working on the Alto protocol side. So I helped create like the Zika Rollup that we are running now on mainnet. And yeah, so we are a layer 2, depth-specific layer 2. And we have been working on some cool features. One that I'll be mainly talking about, the Loopring Bridge, and like the different design patterns which are utilized by the bridge. And also one of the other challenges is, of course, also the block explorer. So we will have a subgraph, which is now still being developed, but it's almost ready, and it's ready enough so people can actually already use it and start building a UI for a block explorer. So yeah, let's start with the presentation about the Loopring Bridge. Let me share my screen. All right. So okay, the Loopring, well, there's Loopring. First, the basic stuff out of the way is Loopring Ziggy Rollup. So we can do only a couple of things. So we can do transfers, we can do order book trading, and we can also do EMM trading, which is already quite a lot. So most people, those are the basic stuff that most people want. And so those are already available completely on layer 2. But sometimes people also want to do other stuff, of course. So there's lots of... yeah. Emily?
Maybe you just want to present full screen. Present full screen.
Present full screen. Okay. Present. Better? Okay. So yeah, there's lots of stuff to do on Ethereum, and if you are on layer 2, then yeah, you probably also want to do some of those things. And the good thing is that most layer 1 applications actually expose functionality by using a token. So if you want to deposit to a vault, and then in most cases you actually get another token in return. So it's basically, it can be done with a trade on layer 2. So yeah, so we can actually use the basic building stuff, that basic blocks that we have on layer 2 to actually do lots of stuff that are still on layer 1 without actually having to migrate everything over to layer 2. And of course, yeah, there will be multiple layer 2s that will be going live now and in the near future. And people will want to move from and to Loopring to and from those other L2s. So otherwise, people have to, like, if they want to move from Loopring to another L2, they would first have to withdraw and then do another deposit to the other L2. And because the gas costs are high, even that could be quite expensive, just doing that for each user independently. So if you have a system where people can actually do lots of stuff together, so we can actually do like one single L1 operation, then yeah, the gas cost savings are high, which is, and then this design is actually called like DeFi pooling in some cases, of a mass migration. So those are the terms that are often used for describing these features. Okay, so the good thing is that we are a Zika Rollup, and the Zika Rollup is actually very well fit for doing these kinds of L1 interactions because we use a validity proofs. So unlike some other L2s, we actually have fast withdrawal times because once a block is on chain and the block is validated with the validity proof, then we are sure that everything is valid, and we can actually change L1 state immediately. So we don't have to wait on any fraud proofs or something like that before we can actually change L1 state. We can do it immediately, and if the validity proof is submitted next to the block, then we can do everything at once. So we can do L2 block validation, and at the same time we can do L1 transactions. So that just makes the design lots easier, because otherwise there's like the extra delay, and there can also be extra reverts. So if a revert is possible with a fraud proof, then yeah, all the L1 interactions that were done need to be reverted as well, which is kind of like yeah, very hard to do. It's also very capital efficient, because yeah, there is no lockup. There doesn't need to be any kind of liquidity providers which can actually do these, which actually provide funds quickly. So with optimistic rollups and even our Zika Rollups, we have like these extra liquidity providers which can make it even faster. But yeah, you need to have those liquidity providers to facilitate that. But with Zika Rollups, those aren't really that important, because the basic flow is actually good enough in most cases, especially if there are a lot of transactions. So in Zika Rollup, you mostly want to wait until you have a lot of, well, quite enough transactions to actually fill a block. So it's yeah, cost effective to submit the block on chain to do everything. But if there are lots of transactions, we can actually submit lots of blocks very quickly, and the delay is very short. But the one caveat is that if we do these L1 transactions next to the L2 transactions, then yeah, if we modify L2 state in some way, which depends on how the L1 interaction finishes. So if you want to swap, let's say 1 ETH for 1 Bitcoin, and we really want that to happen on layer 2, then like yeah, because there is a delay between doing stuff on layer 2 and layer 1, there could be a chance that like the exchange rate already changed once we actually submit the block on layer 1. So if the exchange rate, like let's say 1 ETH is now 2 Bitcoin, then that's a problem, because yeah, if we did the trade on layer 2 for 1 Bitcoin for 1 ETH, then yeah, the extra the difference between the exchange rate needs to come from somewhere. And if we would just like resubmit the block with the updated exchange rate, then we would have to revert state and all that stuff. So it's just much simpler if we can just depend on the L1 state to be deterministic, or if it's not deterministic, use some design which yeah, makes it more deterministic. And these kind of designs, I will talk about these now. So the first naive solutions to get like these DeFi tokens, like vault tokens or other tokens, no matter what, like on layer 2, is to have liquidity providers. So if you want to put some money in Yearn, in a Yearn vault, like you want to put some ETH in a Yearn vault, you will get Y ETH back. And if there is some liquidity provider which just creates all those orders on layer 2, so provides layer 2 directly, then this works. So people can just trade against this liquidity provider and get their Y tokens back. So it's the same thing as just depositing on layer 1 directly. Of course, the main downside of that is that it's quite capital limited, because this liquidity provider needs to have enough funds to actually facilitate all these trades. And it's also quite capital inefficient, because yeah, this liquidity provider needs to have these funds on hand and like do the trades, like do the L1 interactions as needed as they are, as users want to trade on L2. So if you have enough money, it's actually quite a good system, especially on Zika Rollup, because you can move funds around quite quickly. But it's still not that good, because yeah, you really don't want to count too much on liquidity providers if you don't need them. So the first way to solve that is like what we call the single phase converter, is to actually do the trades on layer 2 with flash loans. And in our case, we can actually do flash minting. So the good thing on layer 2 is that we can basically create tokens out of thin air on layer 2, no matter what. So we don't even have to use L1 flash loans on layer 1, or we don't even need to have access to these tokens at all. So these tokens may not even exist on layer 1 or anywhere. We can just increase the balance on layer 2, and as long as we are able to repay that balance, then everything works out fine. So that's what we have also implemented on our Zika Rollup. We can flash mint whatever amount of tokens on layer 2 that we want, and then just a basic constraint that these have to be paid back. So let's say that we want to facilitate lots of trades between a token and the Y token from a urn vault, for example. Then there is some party, which will likely be the block producer, which just bundles all of these transactions together. So without any capital needed, he can just do all these trades by flash minting the necessary amount of Y tokens, then collect all the tokens that these Y tokens need. And so these can be like hundreds or thousands of just simple L2 trades. Then, because the block producer operator has collected all these funds now, these funds can be withdrawn. Then the actual deposits to the L1 debt can be done. So in this case, Yearn, these like let's say there's 100 people that want to put 1 ETH in the Yearn vault. So there's 100 trades between 1 ETH and 1 Y ETH. The operator collected 1 ETH in this case, withdraws this 100 ETH, does the actual conversion to in the Yearn vault. So 100 ETH is swapped against, let's just say, to keep things simple, 100 Y ETH. And then because 100 Y ETH was first minted to facilitate all these trades, the 100 Y ETH can now be used to repay the initial flash mint to make the amount of flash minted 0. So that's of course the important constraint for the flash minting. Everything that was flash minted can be easily repaid like this. So this works for any kind of token. So if there's just one token conversion to one other token conversion, this system works. But there is a problem if the exchange rate isn't that deterministic. So it works well for something that has a fixed exchange rate. So something like ETH, a swap from ETH to wrapped ETH, of course, is a perfect example because that will always work and the exchange rate is fixed. Something like Aave staking, I think, is also always like one Aave token or one staked Aave token. So there are some cases where this works perfectly and it's very efficient. But if the exchange rate can actually change on L1 all the time, then there is a problem because we flash mint some amount of tokens. We withdraw the main token that's used for the swap. And then this exchange rate is done on L1. But we don't know how much tokens we actually get in return for the tokens that we have withdrawn. It can be like exactly the amount that we expected. It can be more than we expected, which is also fine. It can also be less than the amount of tokens that we expect. And then we will have a problem with repaying the amount of tokens that we flash minted. So so either this fails and we have to revert all kinds of stuff. So the block needs to be reverted and we have to recreate the block, regenerate the zero knowledge proof and all that kind of stuff. So we don't want to do that. So if there's too much, if the amount of tokens is not enough, then the converter will also have some extra funds laying around here to help repay the flash minting. But of course, that's also not ideal. So the use case for this is limited if we don't fully control this L1 debt. So if you fully control the L1 debt, there's also no problem because if we do these trades on L2, and we are the only party that actually can change the exchange rate on L1, then it's still fully deterministic. So in that case, there's also no problem. So it can work in quite a lot of cases, but in some cases, like especially with existing L1 dApps on L1, in quite a few cases there are potential problems. So some extra improvements are needed to make it more deterministic. Yeah, maybe I'll pause a little bit to see if there are any questions. If not,
there is a question in the chat.
Let me see. Chat. Okay. Okay, what sort of Zika Rollup tech are you guys using? For example, Zika Sync is using Zika Snarks and Plunks. How is your rollup process different? So we use, well, it's quite similar now to Zika Sync in that we support, we use Zika Snarks, Zika Sync uses Plunk, we still use Grot16 for the proving system. But yeah, otherwise they are quite similar. The main benefits of Plunks is that they only need a universal trusted setup, and we use Grot16, which still needs a circuit-specific trusted setup. Okay, let's continue with the double phase converter, which solves the deterministic part of the exchange. So it may look a little bit more difficult, but it's still quite easy process. It's just doing things twice instead of a single time. So instead of doing the swap immediately from token to Y token, we do the conversion in 2 steps. And to do that, we actually can add like some vault specific logic to the converter. So the first thing we do is actually swap the token for the converter token, which is just a one-to-one exchange ratio. So if you want to put 1 ETH in Yearn, then you will get 1 V ETH for this converter here. So it just like if it and this token just represents your share in the conversion process. So if there are 100 people that want to put 1 ETH in Yearn, then yeah, if you put 1 ETH in and there are 100 people, then you have 1% of the share in this vault, which is still 1 ETH at the time. So that's what happens in the first phase. So you just do one-to-one swap for this vault token, and then which is of course like fully deterministic. The exchange rate is always one-to-one, and that's also the only thing the converter can do. So nobody else can actually access this converter. And then we do the actual L1 interaction. So we go from the token that all these people deposited, we do 1 L1 interactions to do the swap, and then we get the Y token back, and this can be any number. So if there's 100 ETH, then the amount of Y tokens we got might be like 95 Y ETH, or might be 105 Y ETH, but it doesn't matter. It just, it doesn't matter, of course, for the exchange rate, but it doesn't matter for the system, because every user on L2 still has their shared tokens, which are exactly the amount of tokens that they put in. So if you put in 1% of all the ETH, then you will have 1% of all the Y ETH that this converter had converted. So by doing that, all the operations on L2 are fully deterministic in the first phase and the second phase. So because this is like this is a one-to-one ratio, so all the trades here on the left side will be simple, so one-to-one swap, and then all the interactions in the second block that will be created after this L1 interactions was done will also be deterministic, because we will create this block after the actual L1 interaction has been done. So in the second part, we just exchange the shared tokens against the actual tokens the people want. and then withdraw again, use flash minting to aggregate all these trades on layer 2, and give the people the actual token they want. So instead, compared to the single phase converter, this conversion needs 2 phases, and because people always have access to their shared token on L2, even if we wouldn't submit the second block, they can still withdraw their share token to L1 and actually get their Y token back themselves on layer 2. And that could happen if like the operator stops doing things or doesn't actually want to do the second step, like the distribution step. If somebody like the operator doesn't want to do that anymore for whatever reason, then people are still sure that they can get access back to their money. Okay, so let's go to the third design, and this is the design that's actually will be used for the workshop, and that's the Loopring Bridge. So compared to the converters, the converters are limited in a way in that they can only do token swaps, represented in some kind. So that also, it's always the case that one token is exchanged for another token, which is often the case, but sometimes, of course, it's not the case. Let's say you want to move from one rollup, like you want to move from Loopring to another rollup, then you don't swap tokens, you actually move the tokens from one place to the other. And to do that, people can use the bridge design. Instead of doing L2 trades on L2 trades, they actually do a simple L2 transfer to the bridge. And by doing this L2 transfer, they don't just do the L2 transfer immediately like any other kind of L2 transfer. So they do like a conditional transfer to the bridge account. And only when it's actually processed by the bridge, the transfer will be valid. And the bridge will use those L2 transfers to actually do stuff on layer 1. So all these L2, all the users that want to interact with the bridge, first we aggregate all of them. So all these transfers are accumulated in one account. And then we do single withdrawals for each distinct account. So if people want to interact with Yearn, if people want to interact with Uniswap, people want to move to Rollup, it doesn't matter. All the withdrawals are batched together in one withdrawal per token, which makes it very efficient. And then once they are in the bridge, then we actually do the necessary L1 operations. So these connectors are just simple contracts which do the conversion from like the aggregations to the L1 interaction. So if there's like 100 people that want to interact with the Yearn connector, then this Yearn connector will just get as input a list of those 100 users with like address, the token they deposited, and the amount. This connector can do whatever is needed on layer 1. So probably just run over the list, do the L1 interaction one time for all those users, and then redeposit back to the layers, the users on layer 2. And that can be done for any L1 dApp which has the necessary connector. And this connector is very, very easy. So yeah, it's just very efficient because all these connectors actually work on the same bridge contract, and the bridge contract contains all the funds. So once the Yearn connector contract is called, which will mostly be done with a delegate call. So there's delegate calls here to the different connectors. So these can just do whatever logic is needed without having to move funds around a lot. So once they are withdrawn, the connector can be executed with a delegate call. The necessary funds are directly available in this contract. And once the swap is done on this contract, the necessary funds will already be in the bridge, and they can be batch deposited back to the users on layer 2, which is also just done with simple transfers. So all the actual L1 token transfers are batched in a batch deposit, and then all the different users get their money back on layer 2 with simple transfers, which are very cheap. So here's like a different, like a little bit of a different batch deposit line. It's just that these are like interactions that originate from layer 2. So these like layer 2 people want to interact with layer 1, and they can do something like which we call like bridge calls. So they want to actually, they say like, I want to interact with the Yearn connector. Okay, we will just aggregate them all and do those. But there's also, of course, the case where people from other Zika Rollups or other L2s want to join Loopring. And for that, the bridge contract has just a simple function call that's called batch deposit, which takes like just a list of all the deposits that will be handled in the same way like this deposit is done. So if there's 100 ETH for 100 users, then first the 100 ETH will be done by a single deposit to the loop to the exchange contract to the Zika Rollup, and then all those other transfers will be done on layer 2 very cheaply using layer 2 transfers. And so the cost savings here are that every normal deposits that user does is like a full layer 1 transfer. So it's quite expensive. And by using the batch deposits, we only do the costs once for all these users together, and then just cheaper L2 transfers. Okay, let's see, no answers in the chat. Let's continue. Okay, not that much time anymore. So yeah, the converters are very cheap, mostly. So they only need like 1 or 2 L2 trades per user. And the L1 overhead is always the same because all the aggregation is done on L2. And so not much is left to do on layer 1 and next to just the main L1 interactions that's needed. For the bridge account, mostly the same, also like 1 or 2 L2 transfers per user. Also this fixed L1 overhead to do the actual L1 operation. But there's also some extra L1 overhead because some extra aggregation is needed on the bridge contract. So we have to run over all these different bridge interactions and then pass them around to the necessary contracts, which makes it a little bit more expensive, but also much more flexible because the bridge can do more stuff than the converters, which are mainly like token swap batching. The fees, I think I'll skip that, but the fees are like done in a way that makes sense. No, I'll just skip this one because there's not enough time. Okay, the bridge interface is very easy. So to do a batch deposit to the bridge, so people want to move funds from another layer 2 or even a centralized exchange to Loopring, they can just call this batch deposit contract, which will do all these deposits just passed in with a list, very as efficient as possible. So if there's like 1 token that's need to be deposited for this list, one actual deposit will be done, and all the other deposits will be done with layer 2 transfers. But if there are multiple tokens in this list, then multiple deposits will also be done. But the least minimum amount as necessary. For the bridge connectors, there's also just 2 calls and just this main one. Basically, the other one is just for like the fee system, which I'll drop now. But the process calls is just like, okay, all these bridge calls were collected in the bridge, and this function just gets a nicely formatted list sorted on the group, and the group is just like a kind of L1 interaction, and then all the token transfers that were done on layer 2. So it's just what you'd call what you'd expect. So the owner, the token amount, some extra user data. So some extra custom logic can be done per user in the connector, and some less important data. So I'll first a little bit of time. So I'll show a sample first of such a connector. So this is like how you would create like a connection to a Yearn vault, a Uniswap connector, or some kind of like token swap connector. Is you just implement the process calls, you get the groups. The group is like, this is like a swap example, like it mostly follows like a Uniswap layer 1 dApp. So the group is just the EMM that that the user wants to interact with. So if it's ETH against LRC, then this would be the group, and all the users that want to do this ETH LRC swap are aggregated together in this group. So the first thing we do is run over all the groups. We decode which EMM pool that we want to interact with, and then run over all over the transfers that were done by the users. We check what the minimum amount is for the total amount. Like we check what the slippage is basically. So we have like this total combined, which is transferred by users, but every user actually has a custom slippage limit. So we check here if this slippage limit is reached, if it's set. So if the amount that's if the amount that is received by the user is less than expected, then we actually won't do the trade for that user. So we just skip it and we return the user's initial funds instead of the swap token. So that's done here. So we check if it's valid. If it's valid, it's okay. Then we actually do the swap here with the funds from users that that achieved the minimum slippage. And then we run over all the transfers. So if the swap was successful, we transfer the new token out, and with the new amount that was exchanged. But if it's not valid, we just return the amount that the user transfers to the bridge. So this is what I was also talking about, like the deterministic part. So this case can handle both cases. So the swap here with Uniswap or whatever can actually fail, and user tokens will be returned as if. So we don't depend on the swap to actually function correctly. So it can fail, and even if it doesn't fail, we still have this fallback method to with the slippage. So yeah, lots of flexibility there, and not much time anymore. But and then all these resulting transfers are just also returned to the bridge. So most of the implementation details are just handled by the bridge, and you get a nicely formatted input. So the logic can be quite easy. There's also like a migration example, which is basically the same thing, but yeah, because it's a migration sample, you don't actually return any transfers because yeah, funds are moved out of the exchange and none are returned. So that's the main difference. So let's quickly end this workshop. So okay, the main challenge, that's where we have two challenges. The first is the block explorer front end for the Loopring subgraph. So on the Discord, I shared the link with the subgraph. So it's actually failing because there's some problem with yeah, there's a bug in subgraph, but it doesn't matter because it only fails on a block that's quite, yeah, there's enough blocks that are processed, so there's enough state available to actually start building the front end, and the subgraph will be updated once things are fixed, but it's ready to build on whenever you need. And the second is, of course, like use the Loopring Bridge to interact with another rollup or another L1 dApp. So we don't really want to say give too many IDs. So like some, yeah, so you can be creative. So if you think an L1 dApp is very well fit for this kind of system, then yeah, just let us know what you're planning to do, and yeah, we like creativity here. So of course the more basic ones would be like doing a connector for Uniswap, or doing a connector for Yearn vaults, or interacting, like doing a mass migration for something like Hermes, which has support for that. Yeah, lots of possibilities there. Yeah, just don't start doing something that may not work, or we are not that interested in. We have $5,000 in prizes, and there's mostly be like creativity and like how how well the contracts or the web UI is developed. Okay.
Great, thanks so much, Brecht. That was a really great session. And if anybody has questions, don't hesitate to reach out in the sponsor Loopring channel. Yeah, and thanks everybody for joining us today. And yeah, once again, thanks, Brecht.